Surface feature selection was kind of his first step. So when you have this shape into your CAD system, the thing that you need to do is put a boundary around it that allows you to select what you're trying to automatically come up with the shape of. It goes and grabs all of these facets. From those facets, it generates the point cloud. So all of the points of the vertices form this point cloud. From the point cloud, he segments the point cloud by saying, well, I want a plane here, I want a plane in the middle, I want a plane on the right end, and uses some kind of a guide curve that's going to sweep through the point cloud. So he generates section planes and kind of a trajectory that the section planes are going to be swept through. So here's an example of the trajectory. It's going to be straight through. He figures out the max distance. He figures out the kind of number of sections. I'm going to divide this into two. And he takes a reading here and a reading there. And from that, he gets fewer points. And to those fewer points, he ends up putting them into a polar map. And he reduces, again, the number of points. So he averages the points in each of one of these pie sections, which helps him to do a point reduction but still maintain the quality of the point values, the cloud values. And from that, he gets the sampling of points. He then sets up his kind of polar map to it, and the polar map allows him to then say, here is the cross section and the closed points that need to be used to define the shape. The polar map says, here's a point, and a point, and a point. So he's got kind of 4 rectangles that he's going to kind of go through. He looks at the fitness. He says, how does a circle fit this? How does triangles fit this? How does a quadrilateral fit this? You're trying to look for the lowest number to see which one's going to fit the shape best. If you do a topology fitness on the thing, again, the quadrilateral gives you the best. Kind of you're looking for the highest or the best value. And the cross-section shape is what gets swept through the object and extracted. So here are some examples of his result. Simple little cantilever beam up on the top with a point load on it. Topology gave him this result, and with 4 features, he was able to basically eat away and get about 133% on the CAD model. That's this kind of bluish model. CAD model representing the original thing. So was it a little heavier than it should have been? 33% over the optimal. The next example was a beam with a torque on the end of it. The optimization is the second picture in. You can see how 10 features fit very nicely to that. Gave him 158% of the design. The third one, which is the example we just went through, he was able to do that with 3 features, come up with 101% of the model. And hopefully the A-arm that you're all having wonderful experience with. Have you guys started the A-arm? Anybody with results yet? Or are you still getting it set up? Still getting it set up, a few issues with it. Well, as you do that, he took that same part and basically with 2 features went in and came up with 126%. And the question is, well, how long did it take to do all of this stuff? And it took just a matter of minutes going in and clicking, this is the boundary that I want, grab these points, and everything else is automated. So he completed the simple part for his thesis. He completed the parametric. It certainly was moved towards being automatic. He was able to use standard polygons as the cross sections, and he was able to use least squares and volume methods for kind of measuring the fitness of that. So where he wanted to go, but graduated and took a nice paying job, he wanted to go and look at a better way of doing the cross sections. Okay? So if you take this little vase that's laying on its side, if you were to just take and section it, you would put in these kind of uniform section cuts. That was based on his method. But you're going to miss some important features of where it necks down. And so what he wanted to do is basically come up with a way to vary where some of those cross-section cuts actually fell. Okay? And he felt like he could actually do that, calculate the placement much better if it wasn't just divided by the number of sections, but if they looked at curvature issues and things like that. The other thing that he wanted to do is look at the number of cross sections. You know, if you just took 3 cross sections and you looked at those points, you'd end up with something that looked like that, a very poor fit. What he wanted to do is kind of run an algorithm and where it would suggest where the cross sections ought to be placed, asking the question, well, if 3 cross sections doesn't do it, should I insert 1 in between each of those to get a better representation? And he was able to go from a 75% fit to a 95% fit just by being able to adjust where those would actually fit. The last thing that he felt like he needed to put as a recommendation was what happens if you don't have a, what happens if you don't have a part that can be represented by a convex hull, a closed shape? What happens if it actually doubles back on itself? Well, he found that if you did 2 polar maps with a distance in between the centers of both polar maps, he could represent like a kidney bean where it would actually give you a convex and a concave capability in the same feature, the same cross-section, instead of it being totally convex in the shape. And so these things still reside as a very open, challenging problem in industry. Will it be solved? I am absolutely confident in the next 10, maybe 15 years, this will be a solved problem that will just naturally happen inside of the CAD system. You'll import a model directly from OptiStruct or one of the other optimization packages. It will come in and it will automatically fit manufacturable shapes to the voids in that optimized space. And you'll say, gee, I remember talking about this in Dr. Jensen's class. We're glad that it's solved, because right now, this is a manual process. Totally manual process, and you will experience some of the manual process this week in lab as you try and fix your optimized A-arm to a CAD model, either CATIA or NX. Are there any questions? I think that's the last slide. Any questions on kind of what industry is looking for or hoping for? It's an amazing technology that has been developed, but it's only part of a solution. I mean, it does get you a huge reduction in time, a huge reduction in weight, but it's painful getting the shape back into a CAD system. Questions, comments?
So this is all for like some sort of static loading conditions training for that, you know, takes into account dynamic loads, kinematic systems.
Yeah, so there's lots of research that's going on to that, but I don't know of a commercial tool out there that has kind of done that. So when you go to the conferences and kind of listen to what researchers are beginning to lock in, they're all saying, well, this is topology optimization for stress. What is topology optimization for fatigue? What is topology optimization for heat? What is topology optimization for airflow or things like that? And so those things are beginning to be looked at, be researched, but those, I believe, are significantly more challenging than topology for stress. Okay. But that's a good question. Other questions or comments? Yep.
It seems like then after you do the topology optimization, there would still be an amount of testing going on with those dynamic loads, and you still have to do the manual testing.
Yeah, so there's lots of tools that will virtually look at thermal issues, virtually look at dynamic issues. There's tools out there that do it, but right now what you're left to kind of come back and adjust are the shape and size parameters of what you build into your parametric model. So you can say, well, if I add thickness, is that going to stiffen this up so it's not going to vibrate as much? If I thin this down, is it going to allow heat to escape faster? If I do some kind of heat sink kind of design on it, is heat going to flow out of this? So those things are being done, but they're not being done kind of linked to an optimization etching process where it's eating geometry away. So initially, this class doesn't really enjoy HyperWorks because it tends to be kind of a foreign environment. It's not as friendly as your CAD system that you're used to kind of working with and doing things with. But students by the end of the semester have been able to become very comfortable with it, very knowledgeable with it, and it has led to some really great jobs of students just saying, I know how to do this kind of engineering work in this topology optimization space. And so if you talk about it to interviewers, to potential companies or internship places that you go, you'll find that it's a hot button with industry. I mean, the interviewer may not fully appreciate it, but if you bring it up and talk to them about it, they certainly lock onto it. And it's not something that's generally taught in an undergraduate class. It's something that you find a lot in kind of graduate schools around the country. But we think it's important enough to consider it as a design tool. Okay.
Do you know anything about the forces in HyperMesh? Like what units? Sorry, that's what
So HyperMesh is unitless, and so you need to make sure that when you go in there and set up your lengths, widths, heights, loads, things like that, that you are consistent in what you're giving to it.
So if we say a load of 1,000, do we have any idea, like, does that relate to a Newton or something? Or just okay. It's all dimensionless.
It is dimensionless. So if you're putting your model in using inches, and you've described the thing as being 10 inches long, then the load that you're going to be wanting to work with is going to be English units, not metric. Okay, and so it is unitless. You just have to remember to work out the units as you're putting them in. Okay, and just be consistent. Other questions? Right. Hopefully you won't see me, but you will hear me, and you'll see slides and things like that on Thursday. If not, you'll be getting a lecture from Larissa.
How should I go? I haven't touched it.